Welcome everyone to the 2026 Biophotonics Fluorescence Microscopy Summit. Thank you all so much for joining us, and in this session you will hear from Ben Masella, a principal optical engineer at Optikos. Ben earned his doctorate in optics and currently leads optical design, tolerancing, and system development for advanced imaging and metrology solutions at Optikos. Today he joins us to highlight performance requirements for fluorescence imaging. If you have any questions or comments, you can type them right into the Summit chat box that is on your screen, and if you missed part of today's session, you can always come back later and watch it on demand. That's all for me. Ben, we appreciate you for taking the time to join us here at the Biophotonics Fluorescence Microscopy Summit.
Thank you, Jake. So as you just heard, I'm going to be talking about performance requirements for fluorescence imaging today. I'm a principal optical engineer at Optikos. Optikos has been in business for a little over 40 years, working on optical engineering for various customers in a wide variety of applications and fields. And we typically start product development anywhere in the cycle, anywhere from a clean sheet of paper all the way to volume production. And our experience over the last few years, we've done a number of fluorescence imaging systems and been dealing with customers at a wide range of applications, and understanding where requirements meet optical complexity and cost of the final system is a topic of great interest and something I'd like to review today. So starting off, what we're going to talk about is first order aspects of optical systems. So these are the sort of core components that need to be achieved for a given system. So starting with field of view, how big is the image that you're actually going to record? That leads to a couple of different aspects of the optical system. One being the size of the sensor and the magnification. So for a given size on your object, the magnification system is going to deliver that to a particular size on the sensor, and that is going to fully define your field of view. But the magnification is also going to be related to your resolution in terms of the size of a structure mapped onto your sensor and the size of pixels that you're actually sampling that with. So in terms of what is the smallest detail that you can see with your system, you're going to need to pay attention to the pixel size as well as the magnification of the system. And that's going to tell you how well your sensor is sampling some structure and whether it can technically reproduce that. But that doesn't say anything about whether the image produced at that sensor is actually of high quality. That's more related to the optical system itself actually transferring from the object to the image. So when you're looking at the optical system, the numerical aperture as well affects resolution. So that's going to limit the maximum resolution you can achieve. And then for a given numerical aperture, the aberrations over that aperture of that lens are also going to limit your real world resolution. So there's some factors represent how the image is transferred, and others represent how you then sample that and record it. Beyond that, you have parameters like the depth of field or depth of focus. That's how much movement from the best focal plane along the axis of the lens that you can tolerate. Some systems you need to be able to accept some deviation from best focus, and others you may be able to adjust something in the system or refocus in some way, but that will be primarily driven by the numerical aperture of the lens at the focal plane. And so that is again interrelated with resolution and some other parameters here, including the sensitivity. So the photon budget again is is related to numerical aperture and also the pixel size and the illumination of your system. In a fluorescent system, that's talking about excitation and emission. So the amount of energy you actually get to your pixels and can absorb is going to be related to the numerical aperture, and also how much of that light you collect is going to be related to the pixel size. So all these things again interplay with depth of field, resolution, field of view to determine the performance of the actual system. And then finally, we can look at some spectral considerations in terms of, for a fluorescent system, the bandwidth of the excitation or the emission, spectra and their separation, which will relate to a number of things, including how complex the optical system needs to be due to chromatic aberration. So correcting aberrations over a larger band, which includes both the excitation and the emission, can also lead to more complexity. Also, considerations involving the filter separation and your separation between excitation and emission can add complexity to the system there. So zooming in on numerical aperture, the NA of the system limits the best possible optical resolution. The numerical aperture is just a measure of the size of the cone of light coming to focus, either at the object or the image. Typically, we're interested at the object plane in terms of resolution of the sample. At the image plane, you might be interested in how much power is being delivered to the sensor, and we can discuss that later. But the numerical aperture is directly related to what is the smallest spot that can be created or focused at the sample or sensor. And that's directly related to the wavelength of light passing through and the NA itself. Due to diffraction, there's a limit on how small that spot can be, and here it's related to the ratio of the wavelength to the numerical aperture. So a higher NA lens will be able to create a smaller spot and ultimately technically perform at a higher resolution than a lower NA lens. On a commercial objective, this will be labeled typically. So this objective here has a NA of 0.95 that relates to or is related to a angle of that cone of 72 degrees in air, leading to a minimum spot size of about 0.7 microns at 546 nanometers. So that's the smallest spot that lens could possibly make. But aberrations on top of that will limit its actual resolution. But then that's at the sample plane of an objective, and the spot will actually be magnified onto the image plane where it's detected. So an objective like this, 40x, matched with its appropriate tube lens, will give you a 40x magnification, and so that'll be a 28 micron spot on your actual sensor. So you might be wondering, why not just make all lenses high numerical aperture and high resolution? There's some drawbacks to trying to do that. The major one is that it's difficult. The aberrations in rays, correcting aberrations for rays that are at high angles from the image tend to be harder and require more complex lens designs than designing for lower numerical apertures. So a ray towards the optical axis requires less optical power to correct and will experience less aberration. So increasing the numerical aperture of the lens or designing for a high NA requires more complicated designs, more elements, higher precision of those elements, and that all leads to more expensive and complex designs. Another issue is that the depth of field is related to the numerical aperture. So the larger the cone of light that you're making when you're or collecting from an image or from a fluorophore, for example, the faster defocus will actually blur that image. And that's because the cone of light is so large that it diverges very quickly as you move away from best focus. And on top of that, it tends to be difficult to make large working distance objectives with high NA or really any lens. So the issue there is that if you have a very large angle of light that you're trying to collect and you want to be very far from that image plane with your optic, then the optic grows very quickly. So this ends up becoming a little bit untenable in terms of the size of the optics and the complexity of the system that you need to correct for a large working distance. So that's why you typically see high NA microscope objectives, for example, being relatively short working distance and seeing lower numerical apertures with longer working distance lenses. Another issue that comes up with numerical aperture is the impact of additional optics in the converging space. So, for example, cover glass is an important example. if you have even a perfectly flat piece of glass in a converging space, what you get is a refraction through that displaces the image further away from the optic. And this occurs anywhere within the cone of light, but the refraction experienced close to the axis is actually less than that experienced further from the axis. So what you end up with is a displacement of the image as a function of angle within that numerical aperture cone. And that's what we refer to as spherical aberration. So what's happening here is that the just variable refraction across a perfectly flat window can cause a disruption in the imaging quality of the optic, even if the optic itself is perfect. So for high NA systems, they're typically designed with a small amount of the opposite spherical aberration to account for this. But then that objective needs to be matched with a cover glass of a specific thickness or have some adjustability to correct for this. And this isn't limited to cover glasses. It can be a fluid that you're imaging through. It could be turbid media. The amount that that anything within the converging space affects the imaging performance is going to be related to your numerical aperture. So given that there's a lot of issues that can come up with increasing numerical aperture and complexity and cost of the design, as well as some other features that may be not desirable. A good question is how do you know when you have enough resolution for the task at hand? One way to approach this is to look at what is the minimum sample size that you want to be able to resolve, what feature is the smallest that you need to be able to recreate in your image. On the example on the right, we have a couple of cells, and this is a good example where if all you needed to do was determine that there are two cells and that they're separated and roughly where they are, then you don't need enough resolution to see the individual fibers. And so that would be a much less high performing lens than was used to take this image. But if you actually need to see the fiber structure or any of the subcellular structures, then that obviously is going to be a higher NA, higher resolution system. And making sure that you're cutting off the performance or setting performance at a place that's reasonable for your application is important to maintain a reasonable complexity and cost of your system. And once we know what that actual small feature size is, or the separation between features of importance in the image or in the object, we can calculate in object space what the spatial frequency of that structure would be, or how frequently those structures appear across the image. And that's just the inverse of the size of the structure. You can also do that in sensor space. So we could be looking at this from the sensor side in image space. And by just looking at what the size of a pixel is on a particular array, for example, if you've chosen the sensor, you can calculate what the maximum spatial frequency is that the sensor could reproduce. And this is called the Nyquist frequency. So that's just 1 over twice the pixel pitch or the pixel size. And that'll tell you what is the highest frequency or the smallest structure that sensor could accurately reproduce. And anything beyond that is going to be just noise in your image. Now, you probably want to be a little bit higher in terms of sampling than the Nyquist frequency on your object side, just to avoid issues with noise or movement of the sample relative to the sensor. But a good rule of thumb is the Nyquist frequency is certainly the limit of what the sensor could reproduce. Now, once you have either a frequency of interest or highest frequency of interest calculated either from the sample or from your sensor, then we can look at the lens performance across spatial frequency in terms of what we call the modulation transfer function. So the MTF of the system for an optical system is really a measure of how well the system transfers contrast from the object to the image. So there's a certain range of spatial frequencies contained within any spatial object. And the job of the lens is to transfer that information from one plane to another. And the efficiency with which that happens is effectively the MTF. And now for a given sensor, you may not need to worry about the MTF beyond the Nyquist frequency. For example, the Nyquist frequency for a 5 micron pixel in image space would be about 100 cycles per millimeter. So below that is anything we are interested in for that particular sensor. Now, the numerical aperture, again, is going to limit your maximum resolution. In this case, on an MTF plot, that will be the highest line that you see here, which is referred to as the diffraction limit. So no MTF of the lens will be higher than that for this NA. And that would be the absolute ideal goal for an average fluorescence system, for example. And in this case, on this plot, the different colors represent measurements of MTF at different positions on the image or the object. And so you can see that the lens performance can vary significantly away from the center of the axis, or the center of the lens. So also the MTF can be evaluated either in sensor space at the image or in object space, and they are related simply by the magnification. So it'll be the same curve, but it'll be scaled in frequency by the magnification. And the magnification also affects the size of the image, as we know, and but also the numerical aperture of the system. So for the magnification of a finite conjugate system, where you have a finite object at a finite distance from the lens and a finite image, is going to be the just the ratio of the image sizes, the image size to the object size. And in the case of a kind of a standard objective and tube lens pair in a microscope, that's also going to be the ratio of the effective focal length of the tube lens to the objective. That's why the labels on commercial objectives are actually based on specific tube lens focal lengths. So different vendors have a standard focal length for their tube lenses, so that their objectives will give the labeled focal length, the labeled magnification, 40x, 20x, 10x, when paired with their tube lens. But if you pair it with a different tube lens, then the magnification can change. For example, if you have a shorter tube lens, then you'll have lower relative magnification, where the image will be smaller on the sensor, but the numerical aperture will actually be higher. But if you are to pair that same objective with a longer focal length tube lens, then you'd have the beam size doesn't change out of the objective, but the distance to the image increases. So that cone angle of light coming to the image is going to be smaller, which results in a smaller numerical aperture for that system. This can be important because numerical aperture also impacts the amount of power that's being delivered to the sensor. So the irradiance of the fluorescence collection and the fluorescence delivered to the sensor is the power per unit area at the image surface. And this is going to go as the square of the numerical aperture. So it's important to know what the numerical aperture is of your system at the sensor if you want to understand what the sensitivity of your system is going to be. This then allows you to calculate how many photons you're going to have per pixel given a particular pixel size, and relate that to your actual sensitivity of the pixels and the quantum efficiency of the sensor, for example. So for a higher magnification of the system, given a fixed numerical aperture on the objective side, you're going to have a larger image and a smaller NA, which means the light is going to be distributed over a larger area. So this effectively doesn't change the amount of power delivered to the image, it just changes how it's distributed. And so again, this is going to be important for understanding whether you're sensitive enough, whether you have enough excitation, whether you're collecting enough emission for a particular sensor. And that excitation and emission also impacts whether the lens design is complex or whether it can be simplified, and the types of glasses chosen in lens design. So for example, if you are exciting with the same optics that are being used to collect that, the emission of the fluorescence, then those optics have to be corrected over both of those wave bands. And so that ends up adding complexity to the optical design because you're increasing the bandwidth of that over which the system has to perform. As opposed to, for example, on the bottom left here, if you have a excitation source that is not passing through an objective, for example, that objective doesn't need to perform at that wavelength because it'll be blocked by the filter. It's not going to impact the imaging of the emission. Whereas if you are using the objective, and sometimes there's no way around that, using shared optics between the excitation and emission, what that's going to do is then increase the complexity of the objective, as well as restrict some of the materials that can be used in that objective, depending on the wavelengths of the excitation and emission. In some cases, some glasses that are used for optical systems can fluoresce depending on the excitation wavelength, and that can create background, as well as certain epoxies that might be used in doublets or triplets in these systems. So that's something that needs to be accounted for when you're evaluating whether the system needs to be excited through the objective. And this is important because glass selection will eventually affect performance and cost of the system. There's a wide range of glasses available in the visible spectrum. This is an example of what we call a glass map from O'Hara Glass. There's a number of different glass vendors, and they all have similar types of glasses available. And what's important here is that the index of refraction of the glass varies significantly depending on the type of glass that you choose, but also the amount that index of refraction changes over wavelengths, or its dispersion also changes. Also can be tuned by the glass manufacturer. And so this map is how the index and dispersion of the glasses relate to each other. The dispersion is often measured by calculating the Abbe number, which is what's plotted here. And as you go up in Abbe number, you go down to the bottom left corner, and those are very low dispersion glasses, which have high Abbe numbers and tend to be very expensive and potentially hard to source. The same is true of very high index glasses with very low dispersion. You get it up into the top right corner. And so allowing for various glasses or requiring broadband performance tends to lead to more expensive, more harder to source glass, and also limiting that by requiring the excitation to pass through the objective is also a reason why certain designs may be more or less complex than others. So once we've gone through all the first order requirements and decided how well this lens has to perform, what are the options for building a lens like this or an optical system? First, we could source catalog lens assemblies. This is often the lowest cost option, or a reasonable cost at least. And since we can rely on certain vendors to have stock of objectives, tube lenses, things like that, photographic lenses, the delivery tends to be relatively quick. The downside to doing this is that you're kind of limited in the form factor of these lenses. You're limited to the size of the objectives and their parameters. You have a fixed set of optical parameters, focal lengths, NAs to choose from. And then the performance of these systems tends to be mixed, especially away from the center axis of the lens. And even within a certain, not just between units or between different specific lens models, but also within a specific lens model, the variability of performance can be high. Another option is to look at catalog components and build up a system out of individual lenses or mirrors, singlets, doublets, triplets that are available via catalog. This is individual price. This tends to be about a more modest cost and more rapid delivery, again, similar to the catalog assemblies. It also gives you a little bit more flexibility to mix and match optics and create the optical system that you want. But again, the design performance will be limited by your options available, and also the in terms of focal lengths, coatings, sizes. Also, the performance of the final system will usually be limited by the not only the selection, but also the manufacturing tolerances of those components, which tend to be looser than can be achieved with a custom design. And that's where we get to the third option, which is a custom lens assembly. These would be designed specific to an application, and so would meet all requirements necessary and fit into a particular package if possible. And they can be designed to meet a particular performance after assembly. So not just the individual components meeting a particular spec, but the full assembly meeting a spec. And then also having control over the full design lets you use certain techniques that can scale better with larger productions, like molded optics, for example. The downside to this is that the optics tend to be significantly more expensive than a off-the-shelf solution, and the lead time will be longer because there's a design cycle and likely prototyping involved before actually getting to production. So, key takeaways from what we discussed today. Many important optical system parameters are interrelated. Magnification, for example, affects both image size and numerical aperture. The numerical aperture can affect resolution, depth of field or focus, working distance, and the sensitivity of the system. And all these need to be considered when determining what your system specs are going to be. Lens resolution requirements can be based on the application requirements or the limit of the sensor that you're given. The application-based requirements tend to lead to a less overspecified system, and typically one that is as uncomplicated as it can be. I'll put it that way. Excitation and emission geometries can impact glass selection and design constraints, so it's important to know the geometric constraints of the system and know whether the excitation really needs to share optics with the imaging system. And finally, custom optics can provide better performance and design flexibility than commercial options, but the development costs and lead time are significantly higher. So there's a balance there. Often initial prototyping with off-the-shelf optics can get you a proof of concept and hopefully get you on the way to a custom design that really meets your needs. And that's the end of my presentation. Thank you very much for listening.
Thank you so much, Ben, for joining us to set the standard and define performance requirements for fluorescence imaging. Before we wrap up here, I just want to remind everyone in the audience, if you haven't already, you can type your questions and comments into the Summit chat box, and do not worry, if you have not been answered yet, you will be reached via email at a later date. This session is hosted by us at Photonics Media, and we certainly hope you're enjoying the Fluorescence Microscopy Summit. Thank you all so much for joining us.